What's up, guys? Mrs. Thompson here, and today we're covering entropy. This is the second law of thermodynamics. Alright, before we can begin, I have a couple of pictures for you. In this first picture, you have particles of gas. Big blue particles, those are gas. Alright, they're inside of a closed container, and I want to know which one came first. The one that's spread out, or the one that's close together. Alright, so hopefully you said the one that came first is the one that is close together. And then over time, those particles randomly moved around and spread out. We call that randomness of motion of gases, we call that diffusion. Another one, I have some bricks and they were on the back of a truck, and then you toss the bricks off of the truck. Which pile would you most likely produce? The one on the left or the one on the right? Okay, hopefully you said the one on the right. The bricks aren't going to fall into a nice, neat pyramid. They're just not going to do that. The disorder is more probable than order. So it's more likely that it'll be all over the place than it is that it's going to be nice and neat. Alright, so that brings us to entropy. So entropy. Entropy is what we actually use to measure how much chaos or disorder is in the system. How much randomness is there. Entropy gets the symbol S. If something has high entropy, it has high disorder, high randomness. Okay, so if it's very random, high in entropy. If it's really neat and organized, low disorder, then it has very low entropy. Alright, so just to review the first law of thermodynamics, that is that energy can neither be created or destroyed. It simply gets transformed. We call that conservation of energy. That brings us to the second law of thermodynamics, that is the law of disorder. That is that the universe is constantly heading towards maximum disorder. Things don't just naturally fall into a nice, neat, organized pile. You have to put work in to get them to look like that. So it's natural that things fall apart. Okay? That's why you see this picture of entropy. It is all perfect together when it's in the eave, starts to crack, and over time it's kind of spread out. Looks kind of chaotic. Then we need to know what the sign of S would be. So we said S is for entropy. If you have a positive change in entropy, you're increasing the entropy because things are becoming more random. If you have a negative change in entropy, you're decreasing the entropy because they are becoming less random. They are becoming more organized. It's kind of weird to think about it this way. You'll get used to it. You need to know which state of matter has the most entropy and which state of matter has the least entropy. And so since entropy has to do with disorder, the one that has the most disorder would be the one that has the highest entropy. So gas particles moving around like crazy, that would have the most entropy, whereas solid particles kind of stuck together, not moving a whole lot, would have the least entropy because they're the most organized, the least disorder. So least entropy is solid, most entropy gas. And so then the things in between that, well, solid has less entropy than liquid, okay? And then aqueous solutions. So when you have a salt dissolved in water, that salt in the water is actually more unorganized than just the water itself. And then gas. So it goes in this order. Solid, liquid, aqueous, and gas. Okay. In terms of changes of state, so to go from a solid to a liquid, a solid being organized and a liquid being a little less organized, we are increasing in the entropy. Okay? We're causing it to become more spread out. And as those particles move further and further away from each other, they're a little more random and a little more chaotic, so entropy is increasing. In the opposite direction, let's say I'm going from gas to liquid, then gas to liquid would be a decrease in entropy as it becomes less unorganized. Okay, think about it as disorder, less order, disorder, not less order, but less disorder. Okay. All right, other things that can change in entropy that we will be looking at and trying to make predictions for are the dissolving of gas. So if you dissolve a gas in a liquid, it becomes an aqueous solution. And now the gas has less entropy because it's now trapped within the solution instead of floating off everywhere. If you dissolve a solid into a liquid, it will increase the entropy because now those solid particles get broken up and they get spread out in the solution. So you can think of the spreading out of matter as an increase in entropy. All right. The other thing is we may have a reaction where we're not looking at whether it's solid, liquid, gas, or aqueous, and we're just looking at what's going on with the number of particles in it. And so this says, when a reaction results in an increase in the number of particles, entropy increases. That's because those particles are spreading out. They're becoming more of them. What we would do is we would look at the side of the chemical equation that contains more moles. To do that, we have to add up the coefficients for that side. Okay. And then the side with the most moles will have the higher entropy. This is because that same amount of matter is more spread out on that side of the reaction. So if we're looking at this reaction here, there's 2 moles of water, and on this side there's 2 plus 1, there's 3 moles of whatever. We've got hydrogen and oxygen. We have more particles on the right, therefore on the right we have more entropy, more disorder. Alright, another thing that can change it is changing the temperature. If we increase the temperature of any substance, the entropy is going to increase because the particles are moving faster and are spreading apart. Alright, so we're going to do some examples. And we're going to predict what happens to the entropy as these changes take place. Alright, first one. Dry ice undergoes sublimation. Okay. Remember, that's directly from solid to gas. So solid to gas, that's a change in entropy. It increases the disorder. So it would be a positive delta S is what we would write to say increasing in entropy. Alright. Sugar dissolves in water. Now here we have a solid, and now it's going to be something aqueous. And those sugar molecules are dissolved in the water and just floating around and moving all over the place, and now they're higher in entropy. So this is an increase in entropy. Right. You're going to try the next two. Alright. Water freezes at 0 degrees Celsius. So we're going from liquid to solid. And that is a decrease in the disorder. So it's a negative change in entropy. Alright. A supersaturated solution of sodium chloride recrystallizes. Don't worry about that word, supersaturated. Just know that we've got it recrystallizing. Crystallizing, forming solid sodium chloride. So it's going from an aqueous solution to solid. And so that is a negative or a decrease in entropy. It's becoming more organized. Alright, here's another one. An ice cube melts in your hand. Alright, so that's solid to liquid, increase in entropy. E, here we've got nothing but gases. Alright, so one thing I want to make clear that I didn't make clear earlier is that it's the phase change that's the most important. So look there. Okay, look at the phase change first. Then, if they're all the same phase, then you have to look at the number of particles. So if I look at the number of particles here, I've got 2 on the left side plus this one on the left side. So that's 3 moles of gas on the left. And on the right, 2 moles of gas. So it's going from 3 to 2. Okay. It's becoming more organized because it is becoming less moles. So more organized means less disorder, so it's decreasing in entropy. All right, and the next one, what do you think? All right, so in this one we have gas, 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 same thing. And so we have 2 moles of gas on the left, and we still have 2 moles of gas on the right. So what's going on with entropy? Same number of particles, there's no change in entropy. Okay, so I hope predicting changes in entropy isn't difficult for you. We will do some practice in class. I want to leave you with this picture, which is what I blame my term on, I blame entropy, because the second law of thermodynamics says that this is just bound to happen. My room is bound to get messy. All right. I will see you next time. Have a good night.